This is not an equation, right? Like if I give you this, this is not an equation, is it? Now, can I rearrange it? So I'm saying that's equal to this, right? I'm not saying that this is an equation. I'm just saying that this statement is equivalent to, or this expression is equivalent to this expression, which is equivalent to this expression, which is equivalent to this. It's kind of like this. Think of it this way. If I write x squared minus 4 equals 0, that is an equation, right? And you can solve this. But if I just write x squared minus 4, that's an expression. You can't solve this, but you could tell me that that's a difference of squares, right? You could factor it, but that's all you could say. When you put the equals there, then you can start working on both sides of the equation and doing things. Like here you could add 4 to both sides, then you could take the square root on both sides. But you started with an equation, not an expression.
On the other problem, divided by 9, we only have to divide by -1 and cancel out the negative.
It's the same thing. Because this negative became positive, that positive became negative, that positive became negative. Right, so it's the same effect? Is that what you're asking?
Yeah, like, and then after that one, you divide by -1, like -4 divided by -1. Like when you hit the 9 out, we divided like 2 divided by.
Yeah, we had to divide by 9. Look, what would happen if I multiply this through? That, right? Because it's a 1, it doesn't. We're not really dividing by anything.
Okay.
We're just really pulling a negative out. All right, what are these first 3 terms guaranteed to factor to be? X minus 2 squared, okay? So we have here -1 parenthesis, then another set of parentheses, x minus 2, that quantity squared. That takes care of everything in green. What do I still have over here? -9. And let's just leave it like that for a second, because on the last one, remember we pushed the 9 back through and then we wound up taking it back out? Let's just leave it just like this and go back to the original problem now. This is -1 parenthesis, then parenthesis, x minus 2, that quantity squared, and then -9, and then close it, and then dx. So what you have to see here is that if this -1, right, if this -1 wasn't here, then which of, imagine that's not there, which of the forms does it look like? First, second, or third? It would look like the third one, right? Because we have like an x squared minus a squared. Here we would have to do a little u sub first just to get this out of here, right? Because it's linear. But it looks like the third one, right? The problem is we have a negative. And you cannot pull the negative out of the, y'all understand why, right? No?
It's imaginary.
It would be imaginary, right? So we're not dealing with imaginary numbers here. So what's the fix? Distribute it back through, and it just changes the signs of those, doesn't it? It turns into this. Square root. It'll be negative in front of the x minus 2 squared. You can't actually put that negative in. You can't do it because it's squared first. But it becomes +9, doesn't it? dx, right? That's what it becomes. And now just switch the order of these. Put the 9 in front of it. You all see it? If I put the 9 in front, now it looks like this. 9 minus x minus 2, that quantity squared dx. And what formula does that look like? The first one. Do you see? That's how you deal with the negative. You just do all your completing in the square, and at the end, you're going to wind up just like distributing the negative through and flipping them, or changing the order. Okay. Let me just write down what the next step would be. I'm not going to finish this problem. U is x minus 2. Basic u sub. du is dx. The integral is rewritten 1 over the square root 9 minus u squared du. Right, all I'm doing is replacing x minus 2 with u, and then the derivative of that's just dx. Rewrite the integral in terms of u. Then I'm going to do a trig sub. What's my trig sub going to be? I'm using the first one, right? So what is equal to what? A is 3, so 3 sine theta is equal to what? U, right? Not x, right? We're replacing that u right there with u is 3 sine theta, and then you continue. Is that all right? Can I dot, dot, dot this? You would go the rest of the way with this. All right. So that's it for trig sub. Now you just have to go try and do problems, all right? More problems. So now your homework, I told you just do the ones that had the minuses. Now just do as much as you can from that homework now, all right? Now I'm gonna give you a quiz, all right? Not right now, but the quiz is that sheet that I handed out. Does someone have it with them? The sheet that I handed out last time, the photocopy. Was that it? It was the one that had the real, it was just right down the center strip. You see that? That one? If you don't have it, take a picture of your neighbors, all right? So what I'm going to offer, oh, what's that?
I think one.
Oh, one's with the quiz. Okay, yeah, there's mine. So what, Chris, your quiz is here. Anyone else need their quiz from last time? Yeah, this didn't go around. Elijah, right?
Yes.
Okay, you're right there. Okay. You also need it?
Yes.
You, go, it's probably right. There you are. Okay. Mm-hmm. Yes.
My sheet from last time in the quiz pile.
What, this one?
Red circle.
Oh, is this the red one?
Yeah.
Is that yours? Okay, there you go. What? Really? What the hell? Okay, it's all right. Who else? Okay, so here's what I'd like for you to do. On that sheet of paper, right? On that sheet of paper that has all those problems on it, I want you to do any 3 that you want and turn that into me next time. All right? Any 3. No, out of everything there. Any 3 you want. And you know what? I mean, don't take the path of least resistance. You know, don't just do like the easiest ones you can find, or like let me just do the first 3. You know, challenge yourself a little bit to try one that's a little bit harder, you know? Everyone understand the instructions? Pick 3, work them out. Okay, show all your steps. I don't want just answers. Okay, show all your steps. Turn it in beginning of class next time. All right?
So is that a quiz grade?
That'll be a quiz grade. Yep. But don't forget, still be working on your other homework from this section as well. Here, let's make this a little more fun. Hold on, I'm going to make this a little more fun. Let's see. Okay. Right here, from right here, over, your 3 have to come from the evens. And your 3 have to come from the odds. Even. We'll pick, yeah. Evens, odds, okay?
Can you tell me which ones will require completing the square? Because I need to practice completing it.
Anything that has a quadratic that has an x term in it
Okay.
will require completing the square.
All right.
All right, well, we still have a lot of time, so we are going to continue. Continue as in we're going to move on. All right, so this section that we just finished took us, what, like 2.5 days, right? Because I told you in the previous section, 6.2, what was it? It was 6.2. In 6.2, I told you it was 2 main ideas, right? Trig integrals first. How do you do sine, cosine? How do you do tangent, secant? Right, that was the first half. Second half was the trig integrals, the square root of a squared minus x squared, x squared minus a squared, or x squared plus a squared. That's the second half. This next section is kind of the same thing. We're going to spend the first half of it just making sure we know how to handle certain integrals. Like, you already know how to do them, you just don't know that you know how to do them, maybe. All right? So we're going to make sure you know how to do these integrals. That'll be the first half. And then the next half will be, now we do partial fraction decomposition. Partial fraction decomposition is something that is covered normally in pre-calculus, but I know that some pre-calculus instructors, well, I believe that the pre-cal committee of faculty that like control the curriculum of that course, they have removed that from the curriculum. So let's see, does anyone here remember from pre-cal whether or not you did partial? I know I did in my class, but anyone that didn't have me, did you do partial fraction decomposition in pre-cal? Maybe, okay, so I'm going to treat it as if you have not seen it, but I'm gonna go real fast through it, and that'll be next class. So it'll be really, really quick, and it won't be a full treatment of it, so you might need to be doing a little bit of like self-study on that. Yes?
Do you have any videos that you recorded in the past of this?
I think, honestly, why don't we see how next class goes for you? And if it makes sense to you, then you won't need to go get external help on it, right? But if you leave and you're like, I still feel very weird about it, then let's go and find something then.
Okay.
Yeah. Yes?
You also have pre-cal lectures uploaded on YouTube?
I have just like things I did in class as well. Yeah, just like this. But you have to remember, my videos that are online are not like designed like, hi, welcome to calculus. We're going to learn calculus. It's whatever happened in that class, right? So it's not intended for the general viewing of everyone. It's really meant for you. But I keep them there, right? They're still there. So
Do you still have past class? Like, do you still have videos from it?
yeah, it's all still there.
Oh, okay.
Yeah, it goes back to like 16 years.
Yeah, I think it's like 2011.
Yeah. Well, I think, well, no, yeah. Yeah, YouTube used to only allow you to upload 10-minute videos. Yeah, back in the day.
Monetized on YouTube?
I can't be monetized. I don't have enough viewers for it anyway, but I couldn't be because I'm doing it at school. So, no, I just know that, I mean, anything I do at school I can't profit off of, right? If I'm using the facility, if I'm using this, I can't. Yeah.
We won't say anything.
Yeah. I don't, it does. Yeah. Not a whole lot of people love to watch this sort of thing, you know?
What about when you were on Zoom? Were you able to monetize while you were
Because I'm using the college's Zoom account, right? It's all right. It would be pennies, I'm sure. Okay, let's continue. Partial fractions. So what we're going to do first in this, it says here, preliminary things. These are things that we need to know before we even get to the hard stuff in this section. So the first thing is don't forget formula number 17, because we're going to use it quite a bit. Formula 17 says, if you have something like this, or let's say this, those are the exact same integrals, aren't they? Because addition doesn't matter. You can rearrange. Those are the same, right? And according to that formula, this you should be able to get automatically without doing any sort of thinking, all right? It looks like the formula I'm giving you here is 1 over u squared plus a squared du. So what's the variable here, u or a? U, you know that because of the du, right? That the antiderivative of that is 1 over a inverse tangent of u over a plus c. That is a formula we need to know, formula 17. So what's the answer to this? What's a? 3, right? So this is 1/3 inverse tangent of x over 3 plus c, and we're done. See there's no square root? Do y'all see there's no square root here? So it's not the trig sub, right? It's just x squared plus 9. You need to know that. This would be the same exact answer, right? Okay, let me give you a different one. What about this? Well, does it look like that? Does it look like this? Yes, right? In form, it's the same, right? What's a? Square root of 3, right? Square root of 3. So I'm going to write 1 over root 3 inverse tangent of x over root 3 plus c. And I'm done, okay? You do not need to rationalize your denominators here. Just leave it. It's fine. One more. Why did I put the... Because the formula says that this number has to be, that is a squared, right? So if 3 is a squared, then that means a has to be the square root of that number. Just like we had 3 here, right? How do we get 3? What's the square root of 9? It's 3. Good? How about this one? Do you see the thing x plus 3? Do you see this is linear, right? This is linear. So we could, do y'all see that you could do just a basic u sub real quick? If you did a basic u sub, this would become u squared plus a squared, right? Or u squared plus 4. And then we could go to that formula, right? So without really doing much thinking again, what's a here? A. A is 2, so this will become 1/2 inverse tangent of, okay, this is the part that you have to be careful. Because what's the u for us here? X plus 3. So x plus 3 over 2. Plus c, sorry, plus c. These problems should not require any work from us. It should just be a recognition thing. Let's do one more. Change this problem slightly. These are very similar, yes? This is linear, that's linear, so we should be able to do the same thing, with one exception. This has a 5 in front, doesn't it? So how would we deal with, like, how would that be different then? We would have to account for, whatever our answer is, when we took the derivative, when we got to the derivative of what's inside, we'd have a 5 pop out, wouldn't we? I need to kill that 5 off. So I'm going to have to put what out here in front? A 1/5, just to start. That'll kill off the 5 that was here. And now I can just run through the formula. The formula is 1/2 inverse. Why am I using 2? Because a is 2, right? Because the 4. And then this will be 5x plus 1 over 2 plus c. So this is just basic, like here's the formula. That's as easy as it gets. Here, okay, a, be careful, because a is the square root of 3. Here is like, okay, well, if you have a linear expression, then you can just replace that linear expression. But if you have a coefficient in front of the x, you have to account for that in the chain rule, so you have to kill the 5 off with a 1/5. Those are like different sorts of levels of that problem. Understood? All right, that's the first thing we need to know as we move on. All right, the next thing we need to know is how to deal with an integral whenever we have a constant on top of a linear expression. So the form here for number 1 is any integral where the top is a constant and the bottom is linear. Constant, let me put 1, over linear expression, x plus 2 dx. How do we do? You know how to do this already. You just need me to remind you. What would you do? How would you solve that? Basic u sub. What would u be? X plus 2. U would be x plus 2. Du is dx. Rewrite the integral. 1 over u. Dx is du. What's the antiderivative of 1 over u? Natural log absolute value of u plus c. Replace the u with your expression, right? That's just basic u sub, right? Basic u sub. Let's do another one. 3 over x plus 2 dx. What's the only difference between this and the one before? Just take that 3 out first, right? We just pull the 3 out of the integral first. And how would that change our answer? We just have a 3 in front of this, right? That's it. It's the only difference. right? You would take that 3, you'd put the 3 on the outside, you'd change that to a 1, you'd figure out what this is, which is that, and you'd be done. Okay? How about this? Just to check that you know what we're doing here. How about this? You shouldn't have to write anything down for this. You should be able to just say what that answer is. 4 natural log, absolute value, x plus 7, close it, plus c. That's it. Why is this working? Because you're seeing, right? You're seeing that the 4 comes out, then you have 1 over a linear expression, right? 1 over linear. You make your u substitution, you're going to wind up with 1 over u du, and then the antiderivative is natural log. Okay, now I'm going to try and trick you. Put a 3 in front of that x. That changes things a little bit, because when you make your basic u sub, this would be what instead now? 3x plus 1, what would the derivative be? 3 dx, right? And then you'd have to scale, wouldn't you? So it's 1/3, exactly. So now I'm going to have the 1/3 that's going to scale out that that number in front of x. Then I still have natural log of what? 3x plus 1 plus c. I wonder if we could generalize this. Let's see if we can find a general sort of formula for any time we have a constant over a linear expression. So let's see, in general, let's use a constant on top. I don't want to use c because we're going to have a plus c over here. How about I use, you want to use what? N? Okay, I'll use n, even though we usually reserve n for integers, we'll use n. So that's some constant n over, let me show you a linear expression on the bottom, ax plus b. Isn't that linear on the bottom? Okay, what should the antiderivative of this be? Well, the n we could do what with? Just take it out. So there's n. Okay, now this is linear down here, right? So I know I'm going to need a natural log of that ax plus b, right? Plus c. But what am I missing out here? 1 over a. The thing to kill off the a that happens when I take a derivative and have chain rule.
So we just have n over a.
N over a. Yep. Okay. Constant over linear expression, right? Constant over linear expression. We should all be able to handle that without too much thought, right? Do you all agree? Okay, what's the next thing we need to be able to do? Oh, you know what? That's a good example right there. Look at that one right there. Let's go ahead and do that one. What's different here is just that the denominator is linear, right? It is linear, but I kind of rearranged the order. So what's the a for us? What's the a for us here? -5. So it should be n, which is just the 1 on top, 1 over -5, natural log absolute value, 4 minus 5x plus c. All right, constant over linear, we're in business. The next thing, constant over repeated linear. Constant over repeated linear. The goal of this, let me kind of take a step back. The goal of what we're doing right now is to be able to get to something like this and not need to actually write down like a u substitution. Like, you know, u is equal to this, du is equal to blah, 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 then do your u. We're trying to avoid doing that because that's going to add time to the problem. And next class, we're going to see that we're going to work this big problem out and we're going to get it to a bunch of integrals. It's going to be a bunch of different integrals. And each one of them is going to look like one of the ones we're doing right now. So we want to just be able to knock those out without having to like write a bunch of stuff down. So these things are going to be at the end of the problem next class. All right, constant over linear. Next one is constant over repeated linear. So here what I'm saying is, what if this linear expression on the bottom is to a power? So let me just put a 1 up here. What if it's to a power n, right? What if this thing is repeated? That factor is a repeated factor. Look at that one right there. We're not going to get a general formula for this one. We're just going to think through it. Maybe we will do a general formula. I don't know. So there's a constant on top, and on the bottom I have a linear expression that's being repeated. Can we change that to a 3? Let's change it to a 3 so it's not exactly that one. Do you all agree that that is a constant on top, and the bottom is a repeated linear factor? It's a linear factor that's being cubed, so it's repeated. Now, unfortunately, the natural log won't work here, right? The reason natural log works here is because when we replace this with u, or this with u, we get 1 over u. And the antiderivative of 1 over u is natural log. But here, if we do a basic u sub, then it's going to be 1 over u cubed, and that's not natural log, right? The antiderivative. We would have to use the power rule, right? We would have to use the power rule. So I'm actually going to work this out. But everything I write in red here is pretty much what I'm going to be thinking. Like in the future, as I do more of these problems, this is what I'm actually going to be thinking, all right? Is that u here is 2x plus 1. The derivative of that is 2 dx. So I have to scale by a half to rewrite dx. Okay, so that's just my basic u sub. And when I rewrite the integral, I'm going to get a 1 over u cubed du, but I had to have that half in front of the du when I scaled out the 2 that came from this right here, right? And then, to do this, I write u to the negative 3, right? Bring it up as u to the negative 3 so I can use the power rule for antiderivatives. Remember the power rule? 1/2 comes for the ride. Okay, what do we do to this to do the antiderivative? We add 1 to that. So it'll be u to the negative 2 out here, right? But in front of it, you have to put 1 over negative 2. I'm using that formula from way back when. The antiderivative x to the n dx is equal to 1 over n plus 1, x to the n plus 1. This is our power rule for antiderivatives, one of the first things we ever learned. All right, that's exactly what I did there. And so this should become negative 1/4 2x plus 1 to the negative 2 plus c. I should have put plus c here, sorry. And then you could drop that back down, couldn't you? You could drop this back down, maybe write it as negative 1 over 4 times 2x plus 1 squared plus c. Yeah, so I am telling you that everything I wrote there in red is kind of something you want to be able to do mentally. Now, if you need to do it if you actually need to write it down, that's okay, but it's going to slow you down, right? If you have to do that. So let's try another one, okay? Let's try another one of these. Let's try not to write everything down. Let's try and talk through it. In order to do this, right, in order to do what I'm about to do here, I have to have a constant on top and a repeated linear on the bottom. Let's go with a 1 just to make this clean. Let's go 5x plus 2. That's linear. Let's raise it to the 7th power, dx. Okay. So I look at that and I go right away, I'm going to need a 1/5. Why? Because I have a 5 here, right? So I'm going to need a 1/5. That'll kill off that thing. This is really going to look like 1 over u to the 7th. 1 over u to the 7th. 1 over u to the 7th is the same as u to what power? Negative 7. How do you take the antiderivative of u to the negative 7? You add 1, right? So in front of this, I need 1 over what? Negative 6, u, right? U to the negative 6, but what's u for us? 5x plus 2 to the negative 6 plus c. Do you see how I'm not really doing any work there? I'm just thinking through it, right? And then you can clean this up. How about we write, let's put those together. We'll put the negative on top. That'll be a 30, and we'll go 5x plus 2 to the 6th power plus c. So these two are negative 30, but I put the negative on the top instead. I left the 30 here, and then I brought that and dropped it to the bottom. This would be an okay answer on a test, but I'm just saying, like, this does clean up to be that, right? Questions, comments? Oh, shit, are we almost out of time? Damn. One more. Last one. 8 over 4 take away 3x all to the, let's just go 4th power. I have a constant over a repeated linear factor, right? Repeated linear factor. The constant on top this time is not 1, right? It's 8. So that's going to come with me, right? I need the 8. Okay, let's account for this thing in front of the x. Negative 3, so I need a what in front of the antiderivative? Negative 1/3. Okay, so I've accounted for the 8. I've accounted for that negative 3. So when I do the u, right, u is this thing. It'll be 1 over u to the 4th, which is the same as u to the negative 4. And now you do your antiderivative, right? So you add 1. So you'll have here times 1 over negative 3 u to the, oh wait, but what's u? 4 minus 3x to the negative 3 plus a constant. And then you can clean all that up, right? That's 8/9. 8/9, I'll just put 8 over 9, 4 minus 3x to the 3rd plus c. Okay, we still have next class, all right? We still have, that's the 3rd thing you need to know. There's a 4th, a 5th, a 6th, a 7th, an 8th, and then we get to how to integrate those things. See those things? We're going to integrate those. Rational functions. So to do that, we're going to need partial fraction decomposition. Once we do partial fraction decomposition, each one of those integrals is going to look like one of the 8 that I've prefaced this whole thing with. Okay? Your homework for tonight is to go and make sure you've done as much as you possibly can in 6.2, and then to complete 3 problems, evens, odds from the handout. Anybody need the handout? I don't have a physical copy, but did you get a picture or something? Take a picture? If you don't have it, just ask someone around you. Take a picture of it real quick. All right, everyone, have a good rest of your day.
So what you do to 6.2 homework on the schedule?